Let's see. Mute. All right, on the lab tables is a whole bunch of equipment, burettes, solutions, beakers, and stuff like that. And what I want you to do today is what we call a rough titration, or get used to how the procedure works, and not worry about getting data today. So there's 2 pages that you pick up. One says like acid-base titration. The other one is the data table. The data table is where you'll record your data tomorrow in like 2 different trials. Let me tell you about some lab techniques that are good and smart to do. So in the procedure it says, put on goggles. You got to wear goggles, especially because we're working with sodium hydroxide and hydrochloric acid. The equipment's already set up. A few things to know about the equipment. The burettes are just kind of set in the clamps. The burettes themselves are relatively fragile. You don't want to like try to slide the burette up and down inside the clamp. Instead, the clamps are made a couple different ways, but there's a way to release the burette from the clamp. Some of them, you squeeze the little thing here and slide it up and down, or hey.
Hello, Mackenzie?
Yeah.
Okay, thank you.
Yep. This is from like, baseball? What is it? Tennis. You're holding the racket that way. You know what I mean? Yeah. Okay, so let's see. Yeah, you want to adjust the burette to a reasonable height. Like you don't want to have the end of the burette down in the flask, kind of like it's shown here, but you don't want it too high up because then it runs too far down. Okay, there are some beakers that you can label and keep track of stuff. Now, there's an important thing about sometimes it is very important to know or to measure out a particular volume of material. But other times it doesn't matter how much material you use, but you've got to know how much you use. So here's what I mean by that. In the titration in like step number 8, it says use a graduated cylinder to measure out 25 milliliters of HCl. So here's a good technique. If you take a graduated cylinder and there's the position for 25 milliliters, and you try to put exactly 25 milliliters in that graduated cylinder, it's really hard to do. In other words, getting the level of that hydrochloric acid so that it's precisely 25 milliliters is really tough. If you put too much in and you try to pour some out, a whole bunch comes out at once, or if you try to put some more in, the level will go up dramatically. So here's the thing. You want about 25 milliliters. It doesn't matter how much you use, but you need to record exactly how much you actually use. What I'm trying to say there is don't try to get it to 25 milliliters. Instead, put some stuff in the graduated cylinder. And if it comes to here, a little bit less than 25, that's okay. Maybe then you read it's 23.78 milliliters. So what's important is that you're about 25 milliliters. Could be less, could be more. Maybe you're up here, 25, even like 29.7 milliliters would be just fine. Actually, our graduated cylinder is only good to the nearest tenth of a milliliter. So you want to know the volume very precisely, but it doesn't have to be 25. Because you know the concentration of this, if it's 0.5 molar, and then you know what volume you use, you can calculate the number of moles, because the number of moles is equal to the molarity times the volume. So you just take the molarity and multiply it by whatever volume you use, and that's the number of moles of acid that's actually inside the cylinder. It's simply a waste of time to try to use a particular volume. We do have burettes that are designed to dispense very exact amounts of fluid. There are volumetric pipettes that you can use to suck up particular volumes of fluid. But oftentimes in the laboratory, if it doesn't matter the exact number of moles that you're actually using, then just throw some in the cylinder, measure the volume precisely, do the math, and that'll tell you how many moles happen to be in there. So each trial will be a little bit different because you'll have a slightly different volume to start with. Anyway, this hydrochloric acid is a standard solution. It says 0.5 molar, but it's actually about as close to 0.5 as you could possibly get. It's like 0.5000 molar. The hydrochloric acid has been diluted very precisely. So the molarity of the hydrochloric acid is very well known, and the volume you can then just read. So what goes in the burette is sodium hydroxide. Now in the procedure, and I mentioned this, you want to wash the burette with sodium hydroxide first. What that procedure doesn't mean is you don't fill the burette entirely with sodium hydroxide and then run sodium hydroxide through it. Instead, to prime the burette or make sure that the burette, once it's cleaned, if it had any water in it, the first part about putting sodium hydroxide in the burette just means to pour some down through the top while you have the stopcock open and allow the sodium hydroxide to run down along the sides. And that way, any water that happens to be along the insides of the burette from a previous cleaning will end up getting washed down through and into the waste container. Because you don't want to change the concentration of the sodium hydroxide you put into the burette by having excess water that was left over from previous cleaning come into contact with sodium hydroxide. Now, to be honest, these are already dry, so you shouldn't have any trouble, but there could be some residue from a previous experiment, because what happens is if they're not cleaned well, sodium hydroxide is a base in solution, but if you get rid of the water, it ends up to form a solid. In fact, some of the materials, because they were used on Monday in a different class, if they weren't cleaned entirely, you might notice like a white film, because when you have a solution of sodium hydroxide and the water evaporates away, it leaves a film of solid sodium hydroxide. We buy sodium hydroxide as a solid. It's sold in pellets, like round pellets. That's kind of like, they actually look like Dippin' Dots, but they're at room temperature. They're not frozen. They're just like little round dots. All right, so anyway, the other thing about the procedure says, when you fill the burette up, you want to get up to about the 0 mark. You don't have to have the burette exactly at the 0 mark to start. That doesn't really matter. If you fill the burette and it starts out somewhere, maybe here like 6.25 milliliters, that's okay. You just can't start with the sodium hydroxide above the 0, because then you don't know how much you've delivered. Instead, you want the sodium hydroxide to start at the 0 or somewhere below the 0. So if you put too much sodium hydroxide in and it's above the 0 mark, just run the burette a little bit until the level of sodium hydroxide ends up at the 0 mark, and then you can start at 0. But the whole principle with running a burette for titration is, if you start with 6.25 milliliters is the mark initially, and you use some sodium hydroxide, and maybe it gets down to like 27.20 milliliters, the volume that you use is the difference between those volumes. And you don't have to fill the burette back up, because you can see here I used about 21 milliliters. There's still another 21 milliliters of solution in here or more. So if you do another trial, it might get down to somewhere else, like 48.2 milliliters or something like that. So you can get multiple trials out of one filling of the burette. What's important is that you record where the level of the sodium hydroxide is at the beginning of a trial and where it is at the end of the trial, and subtracting those levels gets you the volume that was dispensed. And then if it's here and you're going to use about 20 or whatever, and there's 27 left in there, you can do another trial and then just subtract these amounts to get the next amount. All right, so here's really what I want you to do, is try to get a rough estimate of what the concentration of the unknown is. And tomorrow, the bottle you have will have a different concentration, but the plan is to see what the endpoint looks like. So when you put the hydrochloric acid in the flask, you also need to add phenolphthalein, and it'll start out as a colorless solution. And as you add sodium hydroxide, you'll see as the sodium hydroxide hits the water, wherever it hits the solution, it'll turn pink, but then as you swirl it around, it'll go back to colorless. You're trying to get to that end point, that place where the solution is a very, very, very faint pink, barely noticeable as the faintest light pink color you can get. If it's dark pink all the way through, you went too far. And if you go too far, then that whole trial is done. You throw everything down the drain and you start over again. So all the materials in this lab is totally safe to go down the drain. Hydrochloric acid is a very common acid. This just adds chloride ions to the Susquehanna River, goes down to the ocean and just makes more chlorine ions in the ocean. There's lots of chlorine ions in the ocean. Same with sodium hydroxide. The sodium hydroxide actually acts as a drain cleaner. So you're doing the school a favor by running the sodium hydroxide down the drain, because it'll help to clear up any kind of grease or fat or oil or any kind of crap that's in traps of drains. So sodium hydroxide is really never toxic waste going down drains. You're doing the drains a favor. You know, you can buy drain cleaner sometimes is just concentrated sodium hydroxide. You throw it in the drain and it makes a soap, and it cleans the drains out. Anyway, on the middle lab table, there's goggles, and there's also gloves if you want to wear gloves. Just if you get anything on your hand, just wash your hands out. Everything can go down the drain. So really what I'm looking to do is have you practice putting the equipment together, running some trials, getting to that pink color. So try through the procedure a couple times, see what you can do. And if you're remote, I have a thing for you to watch, because students are practicing the experiment in class. Let me show you where you need to see something here. So there's a video that's posted in the plan for the week that describes how to see the endpoint in titration. So here, if you're in materials and you are in Unit 9 and go to the plan for the week, current week, here it says schedule for the week of 5/10 to 5/14. For today, it says remote student activity. You can either click that here, or it's also in the bottom of the folder for the week right now. It says introduction to titrations on 5/13. So that's today's date, remote or absent students. So if you're remote, it says here, so watch the following video. You can stop at 4:57, summarize procedure for successful titrations. That's all as far as you got to see. So the video is right in the browser, but you can also watch it on YouTube if you want to watch it full screen. It shows the procedure of titration, and it's kind of long, but if you watch the first 5 minutes of it, that would be great. And then you can add it into the discussion. How many decimal places should volumes be recorded to? And what's the benefit of doing a rough titration before the actual trials? So students in class are doing a rough titration, really to try to figure out the approximate volume that's needed to get to the endpoint. By figuring out the approximate volume to get to the endpoint, the video talks about how that can make the laboratory experience go faster and kind of automate titration procedures. So just like how students are practicing in class, this video gives a good overview of what they're seeing in class in the lab, because you don't have the equipment at home. So that's that for today. Let's see.